In this problem, we're being given the graph of a function, and then we're being asked to determine all sorts of information about it. And the first couple of these are not too tough. We'll go through these one by one, and I'll show you the methods for each. A here says the function is decreasing over which intervals. So a function is increasing if it's going up as you go to the right, and it's decreasing if it's going down as you go to the right. So right here, it's decreasing, then it goes up again. Right here, it's decreasing, then it goes up again. So it looks like those are the only two intervals where the function is decreasing. So what is that, from -6, or sorry, -7 to -3? So right there. And then from 2 to 5, so there. And on the rest of those intervals, it would be decreasing. The second part here says the function has local minima at which x values. So a local minima is the bottom of a hill. So the point where to the left and to the right, the function starts to rise again. So a local minima is right here. Another local minima is right here. The minimum for the whole function is going to be way down here at -infinity, but here and here, these are the neighborhood low spots. So this is at the points -3 and 5. All right. C says, what is the sign of the leading coefficient? So this we can tell from looking at the graph, and what I want to do is just put up a couple of simpler examples. A function can be even or odd. Here's an example of an even function. We call it an even function because the highest power of x is an even number. In this case, 2. So this is the function x squared. It's a parabola. And what you see is that an even function, if it's got a positive coefficient, both of the arms point up. Negative x squared, of course, would look like this, and both of the arms would point down. So that's how it works for even functions. You can tell in this function right here, one arm's pointing down, one arm's pointing up. So we have an odd function, and that's good for us to know. It'll help us out later on. So this is an odd function, which means its power, its degree, is going to be some odd number. And I'll put a simpler odd function up here. Here is the cubic function. This is a positive x cubed. And a negative x cubed would be the opposite of that. It would come down and go like that. So this is negative x cubed. And all even and odd functions basically follow these patterns. They just have a little more squiggles in between. So this one, you can see it goes up from the left and then up to the right, which is just like this one. So this is a positive coefficient for an odd function. All right, lastly here it says, which of the following is a possibility for the degree of f? So we want to know what's the highest power of x in this function. And the rule we use here is that the number of bumps on this plus 1 is going to be the lowest possible degree. So I'm going to count all the local minima and local maxima. So here's a local maximum, here's a local maximum. That's all we have in terms of bumps. So that's 4 bumps. We have to add 1. So 5 is the lowest possible. But with all of these functions, it could be that they're a higher degree of the same oddness or evenness, because sometimes those little features, sometimes the bumps are too small, sometimes you have 2 bumps that occur at the same spot and you can't really see them because they just look like a flattening. So this could be a 5th degree function, or it could be some odd degree that's higher than that. So I'd go ahead and check 7 and 9 as well. Same thing works with an even function. If you find that a function is a 4th degree, it could also probably be a 6th degree or an 8th degree. So you'd want to check all 3 of those. But we don't check anything lower than a 5th degree because that's what this rule determines is the lowest possible degree of the function. So that's a little bit of work with inferring some properties from a graph of a function.